Welcome everybody to another session from Network Research. I'm Sridhar here, and today in this special session we are going to brief you about what is periodic energy decomposition analysis and how we can brief all these terminologies on band problem. So PEDA or periodic energy decomposition analysis is the context of periodic systems, particularly when performed with a band program, which is a powerful computational chemistry tool to understand the nature of chemical bonding and interactions in extended materials. So how we can use PEDA in a band environment? So actually, what is PEDA? It is actually the extension of traditional energy decomposition analysis, or EDA, which was originally developed for molecular systems. So the core idea of PEDA is to dissect the total binding or interaction energy between two or more fragments within a periodic system into physically meaningful components. This allows the users to quantify the relative contributions of different types of interactions. So the image which you are seeing in this window, it shows the story, or it tells the story about how we can do the necessary calculations on periodic energy decomposition analysis. So before proceeding to that, I need to brief you that actually what are the terminologies behind this analyzing these different types of interactions. The first one is the preparation energy. Actually, the energy required to distort the isolated fragments from their optimized gas phase geometries to a geometry they adopt in the interacting periodic system. So this term accounts for the strain or deformation energy imposed on the fragment upon interaction. And the next important terminology is the electrostatic interaction. And this term represents the classical Coulombic interaction between the unperturbed charge distributions of the fragments, which often be more attractive and signifies the ionic or polar contributions to the specific bond. And then Pauli's repulsion. So this term briefs about the Pauli's exclusion principle and describes the destabilizing interaction between occupied orbitals of the fragments when they approach each other. So it is a repulsive force that prevents atomic collapse, and then orbital relaxation or interaction. This is a crucial term that accounts for the stabilization gained from orbital mixing or charge transfer or even polarization between the fragments. And it encompasses the formulation of new chemical bonds, either covalent or dative, and changes in the electron density due to the interaction. And then dispersion interaction. So this term often added as a separate correction. For example, Grimm's P3, which can account for a long range or attractive van der Waals forces that are not fully captured by standard DFT functions. And then comes total binding energy or interaction energy, which can be expressed as a sum of all these terms, like preparation energy, then electrostatic energy, Pauli's, and then orbital energy, etc. So by analyzing the magnitude and sign of the individual energy terms, we can gain the deep insights into the nature of the bonding in complex periodic systems, such as adsorption of molecules on surfaces, interlayer interaction in 2D materials, bonding within crystal structures, understanding catalytic mechanism at interfaces. So these are some of the examples which we are going to focus in the coming lectures. And adsorption of molecules on surfaces with carbon monoxide and on MgO have been taken for this specific briefing. So you can see how it will work in the coming videos. So then how we can utilize band for this periodic energy decomposition analysis. That band, we have already briefed multiple applications earlier in our videos, especially for this typical application. It is the periodic density functional program within the AMS environment, which is designed specifically for periodic systems, including crystals, slab, polymers, nanotubes. So it is known for the use of numerical atomic orbitals, which can provide accurate total energies and offer distinct advantages over various analysis. And how we can facilitate for periodic systems, for example, the plane wave ports, we have this atomic orbital approach, which naturally lends itself to fragment-based analysis like EDA. It allows for a more direct interpretation of electron density changes in terms of atomic contributions. Then fragment definition. In band, we can define the system of interest into physically meaningful fragments. For example, a molecule adsorbed on a surface or two layers of a material. This can be done with the graphical user interface or input file. And then fragment calculations. So band can perform the calculations on the isolated fragments or in the distorted geometries as found in the combined system and on the interacting combined periodic system. And then the energy decomposition. So band employs an energy decomposition that systematically breaks down the interaction energy based on the defined fragments, which involves Rosen fragment interaction, orbital mixing, distribution correction, and the visualization. So the key advantages of band for PDA, obviously the atomic orbital basis, and then relativistic effects, which can efficiently and accurately treat relativistic effects, for example, SORA, which is important for systems containing heavy elements, then diverse system types, which handles one-dimensional, two-dimensional, and three-dimensional periodic systems. Comprehensive analysis tools beyond PDA band can offer various analysis options, including density of state band structures and crystal orbit overlap population. And as briefed earlier, we have AMS GUI, which makes setting up and analyzing the periodic energy decomposition calculations more intuitive. So to summarize, PDA with the band is a powerful methodology for gaining fundamental insights into the nature of chemical bonding in a wide range of periodic materials, enabling users to interpret complex quantum mechanical calculations in terms of readily understandable chemical concepts. So just now I'm winding up this session, and I request you to please subscribe our channel, and for more information you can follow our LinkedIn page, Nairo Research India. Thank you.